Sounds good. All right, so this was the mock final, so it only went over the first, like the pre-mock was like from the first two exams, all the material from the first two exams, and this one was like everything after those first two exams. So like things from the third and fourth exam, and then also like stuff that you'd have over afterwards. So I'm gonna go through it because I know it's 40 questions, and then if you have any other questions, we can go over at the end as well. How was this one? Was it okay? Was it easier to remember this stuff than it was to remember the stuff from the first exam? Or like for from the first two exams? It was all right. I know it's just so much material to remember. Huh, okay. Well, all right. Hopefully everything will make sense now once we go over it. I guess this one had a lot of like like all the acids and bases were on this one. Yeah, so I guess it was a lot of stuff on this one. Okay, so the first question was about whether or not a precipitate would form. And so that goes back to like the KSP stuff. So if you remember, if Q is greater than K, so K is like the breaking point when like everything is like perfectly, the reactions rates are exactly the same in both directions, nothing is dissolving anymore and nothing is forming anymore. And so the K value is like the breaking point between like where there is like if you add any more in, there's no precipitation. Or sorry, if you add any more in, there will be precipitation. If you take any out, there's going to be like additional dissolution. And so if Q equals K, it's just like the breaking point between the two. If you have Q is greater than K, that means that your reactant or your products, because your K expression is products of a reactants like you see over here. So if your Q is greater than your K, it means that you need to shift towards the reactant and produce more of the precipitate. And so this is when a precipitate forms. And if Q is less than K, then it's a less than sign. If Q is less than K, then it'll dissolve more. And so in order to determine whether or not a precipitate was going to form, you had to plug these values. I guess there were kind of two steps to do. You had to plug these values into a KSP expression, and then to actually write the KSP expression first. And then after that, you had to determine whether or not the KSP was going to be greater than Q, or whether Q was greater than KSP. So for this reaction, one of the most difficult parts of this question, I think, because the calculation is pretty straightforward, is determining what precipitate is going to form. So in order to know if you have to square something or whatever, you have to know which, like if you were thinking, oh, NaNO3 is my precipitate, then you wouldn't have to square anything, you would just plug those concentrations in. But if CaF2 is what your precipitate is, then you have to actually square something. And so in this case, if you remember your solubility rules from like last semester, and hopefully it's kind of just like ingrained in your brain at this point, like sodium and nitrate are both super duper soluble and like almost always exist as aqueous within solutions. But CaF2 is a precipitate. And so the like compound that you're working with here is CaF2. So your KSP, the chemical reaction that your KSP is based off of, is CaF2 going to Ca2 plus and to F minus. And so when you actually write your KSP expression, you have to make sure, or your Q expression for your KSP, you have to make sure that you're squaring that F value because you have a coefficient of 2 in there. And then you can plug it into your Q equation, and you'll get a value of 2.25 times 10 to the negative 6. So when you compare Q to K, Q is very clearly larger than K. And so because of that, since your K is products over reactants, and it's going to want to go towards equilibrium when Q equals K. That means that you're going to want to go shift back to the CaF2 where it's solid in order to decrease the concentration of the product C of the Ca2 plus and the 2F minus. And so a precipitate is going to form and it would be CaF2. Any questions on that one? Okay. Then this one was just writing the balanced expression or balanced like chemical equation and expression for BaSO4. And so this is supposed to be an arrow here. And so when you do this, BaSO4 is going to just dissolve into Ba2 plus and SO4 2 minus. And then your KSP would just be Ba2 plus times SO4 2 minus. Any questions about that one? Okay, sounds good. All right, so now we have a molar solubility one. So it's kind of the flip thing. So like what you've been doing like before is like kind of plugging in different chemical or different like concentrations in order to like compare to the KSP. But here you're trying to determine what the molar solubility of AgBr is now. And so you have your KSP, so you have to make sure that you write the correct expression. So it's just KSP is Ag plus times Br minus, and so you'll have S squared. And then so just the square root this KSP value, and you should get 7.31 times 10 to the negative 7th as your molar solubility. Any questions on that one? Okay, so now we have kind of the flip thing. So you were given the KSP in the last one and you were trying to solve for molar solubility, and now it's the flip where you're given the molar solubility of MgF2 and you're trying to calculate the KSP of this molecule. And so for MgF2, you'd have MgF2 and it's solid going to Mg2 plus and 2F minus. And so if you remember when you write your Q expression, you have to remember that because you have that coefficient of 2 in front of the F, you need to make sure that you're squaring your F. And so that's probably the most like difficult thing to remember here. So if you see this, you'll have KSP equals Mg squared times F squared. And the molar solubility is just like your S value, so it'll turn to 4S cubed. And then you have your molar solubility, so you can plug that in and you'll get a KSP value of 7.44 times 10 to the negative 11th. Any questions on that one? Okay, we're almost done with molar solubility. I think there's like 2 more. Okay, so the next one is probably the most complicated molar solubility one on this mock final, in my opinion at least. So you're given that the solubility of copper chloride is 3.91 milligrams per 100 milliliters of solution, and then asks you to calculate the KSP. So a really important thing that you have to understand here is that when you're given like your KSP and you solve for S and you get it in a concentration of, or I guess like when you solve for S, like how you did up here, you have to make sure that you're understanding that it's measured in molarity, so it's measured in concentration. And so essentially here they're giving you a mass, they're giving you your molar solubility, but instead of giving it to you in moles over liters, they're giving it to you in milligrams per milliliters. But because you know that this is copper chloride, you can convert this into moles per liter to get the concentration, and then plug it into a KSP expression in order to actually solve for your KSP. So if we start off by trying to solve for the molar solubility in terms of concentration, you're told that your volume was 100 milliliters, so to convert that into liters, so it would be 0.1 liters. Your mass of CuCl is 3.91 milligrams. So again, you have to convert that into grams in order to convert to moles. And then if you find the molar mass of CuCl, it's 99 grams per mole. And so when you actually do the calculation, you should get 3.95 times 10 to the negative fifth moles of CuCl. And so you have your moles of CuCl and you have your volume. So you can just divide your moles by your volume in order to get 3.95 times 10 to the negative fourth molar. So even it's written as moles per liter right now, but you know that that's molar. And so when you have your KSP expression here, it's just CuCl. So it's just like, it'll just be S squared, and you have your S right here. So you just plug that into S squared and you get 1.56 times 10 to the negative 7. I think that this one isn't such a difficult calculation, but it's getting over the idea that they're providing the molar solubility to you in terms of milligrams per milliliters and making that connection that's like, oh, I have to just convert that into molarity. But once you do that, it's kind of the same thing as like this one, for example. Any questions on that? Okay, I think that all of you guys were at the review session last night, I think. And so we went over one that was really similar to this one, just not quite this problem. And it's the selective precipitation. And so the idea here is that you have two different substances. Oh no, I did not give you, I didn't give you guys your KSP values. Okay, well, hopefully you're able to pull up the chart and textbook with your KSP values. I'm really sorry about that. So you have your KSPs. I'm sorry that I didn't provide them to you. I should have done that. Okay, so you have your KSP values and you have to figure out which one precipitates out first. And so it's really important to have the KSP values here in order to determine which one's going to precipitate out first. And so the KSP value of FeCO3 is 3.07 times 10 to the negative 11th. And then the KSP of MgCO3 is 6.82 times 10 to the negative 6th. And so because FeCO3 has such a lower KSP than MgCO3, it means that FeCO3 is going to precipitate out first because you have really similar initial concentrations of them, but their orders of magnitude different in KSPs. And so a smaller concentration of CO3 2 minus is going to reach that KSP further and break that barrier between like when Q becomes greater than K and actually start precipitating out. And so here you have, you know that FeCO3 is going to precipitate out first, and he's asking you to calculate how much iron is going to be, or how much CO3 needs to be present before that iron carbonate starts to precipitate out first. And so in order to do that, you just have to plug in the concentration of iron and multiply it by your, and divide your KSP by your concentration of iron to isolate that FeCO3. And so okay, so for this one, I don't know why I just didn't have the solution for the first part. So for the solution for the first part, then you have, you have to do your KSP. So you'd have your KSP equals Fe2 plus times CO3 2 minus. And so you have to plug in, you have your KSP value as 3.07 times 10 to the negative 11. And that would always be provided to an exam. I'm really sorry it's not here. And then you have your concentration of iron as 0.022 molar. And so when you do the calculation here, you just divide your KSP by that concentration of iron. And that should give you um, 1.39 times 10, or actually 1.4 times 10 to the negative 9th molar. So that's how much carbonate would have to be added before the iron carbonate starts precipitating out. So now it's asking you, okay, once the other cation, once the MgCO3 starts to precipitate out, how much iron is going to be left in the solution here. And so in order to do this, you just have to do the same thing that we just did for the iron, but you do it for magnesium instead. And so you just do your KSP value, your 6.826 times 10 to the negative 6, divided by your 0.014 molar Mg2 plus. And so once you do that, you'll get an iron concentration of, so I think this just got out of order here. So you'll have, this is what the stuff on. So it's like, so you do your, you have your setup here, and then you just do the calculation. And so once you do the calculation with the KSP of magnesium carbonate, you'll get a new carbonate concentration of 4.87 times 10 to the negative 4th. Now that's way higher than the amount of carbonate that's required in order to precipitate out your iron carbonate. And so the whole time that this, when you've been adding more carbonate before your magnesium carbonate starts to precipitate out, this iron carbonate has already been precipitating out. It's already been like decreasing in concentration. The iron's been decreasing in its concentration. So now you can go back to your KSP expression for iron, and you can plug in your new concentration of carbonate that you just got that is like required to make the magnesium carbonate precipitate out. And then you have your KSP value of iron. So again, you just divide your KSP by the concentration of carbonate that you have, and you'll get a remaining concentration of iron as 6.3 times 10 to the negative 8th molar. Any questions about that one?
Yeah, I have a question.
Yeah.
For questions like this, like on the final, would they ever like give us like how it is like here, and then like we have to find the KSPs? Like, is there like a chart or something with the KSPs?
There is a chart in the textbook with the KSPs, but that was just totally my fault for not including it. I think they would always give it to you on the exam. There is a chart in the textbook that I could send you guys just in case, and it might also be helpful to know like which ones are common precipitates. So here's like all of your all your KFs, and then there's another one in the textbook that has all of your KSP values. So I can email this to you guys if you want, but it's also just in the textbook. You can just screenshot if you want. But I think they would always provide them to you. It was just my fault for not including it in there.
Okay, no problem. Thank you.
Okay, so just this one. So now we have a solution is made, 1.1 times 10 to the negative 3rd, Zn 032, and 0.15 molar NH3. And it asks how much zinc remains after the solution goes to equilibrium. So we went over this in study group, or in non-study group, like the review last night, but I'll go over it again really quick too. The whole idea here is that your KF expression is going to be zinc, like the zinc, like zinc NH3 for 2+. And so you're just told that that is your, that's your complex ion. And so that's your complex ion. And then you have your concentrations of zinc and NH3 and so in order to solve for zinc, because the zinc concentration can't be 0, because if the zinc concentration is 0, this whole thing goes to infinity, and then naturally it would produce more zinc. And so basically you're never going to have exactly 0 zinc. You're always going to have some zinc. It'll just be a really low concentration. And so when you plug in X for this expression, but plug in, if you were to do an ice table first here, and you were to figure out the concentrations, you would know that the zinc was the limiting reactant because it's only 1.1 times 10 to the negative 3 as opposed to the 0.15 molar NH3. So even though the NH3 uses 4 moles for every 1 mole of zinc, it doesn't really matter because the concentration of the NH3 is so much higher than the zinc here. And so when you do your ice table, you would have the zinc plus 4 NH3 forms the zinc and H3 for 2+. And so the idea here is that this is your limiting reactant, so you have 1.1 times 10 to the negative third. And almost all of that would get used up. And so at equilibrium, you'll have X, but X should be close to 0. And then for NH3, you start with 0.15. And so to get this 0.1456 number, you'd end up having to subtract 4 times 1.1 times 10 to the negative 3, because for every 1 mole of zinc, there are 4 moles of this NH3 that get used up. And then you would add this 1.1 number to this, and that's where the numerator comes from. And so once you do this, then you should get, and you plug it into the equation here, you just solve for X, so you would multiply by this 0.14 number, and then you would, and you could divide all of this. You could divide the 1.1. So your final calculation would be 1.1 times 10 to the negative third divided by this 2.8 times 10 to the negative 9 or 10 to the 9, which is your Kf value, times your concentration of NH3 to the 4th power, because there's 4 as the stoichiometric coefficient. And so you'll get a zinc concentration of 8.7 times 10 to the negative 10. And you can also like kind of do a mental check where like, yes, it's like super small, so it makes sense in this scenario. If you ever got a concentration like wasn't that small, it wouldn't make sense, and you would know that you had messed something up in your calculation. So now that's like all the KSP, KF type problems, and now we'll kind of transition back into like acids and base stuff. And so your first question is for like the acids and bases was asking about a stronger base, S2 versus Se2. And so there's 2 ways you can think about this. Let me pull up the periodic table. So there's 2 ways I think you can think about this. You have, first, you know that for the weaker acid is going to have the stronger conjugate. So it's one way you could think of it. So you could first determine the stronger acid and then go from there. And that's kind of like how the book explains it. So for example, here, H2SE is going to be the stronger acid because it's a larger atom, and so it'll be able to lose that electron more easily. And so sulfur H2S would be the weaker acid. And so you could go that way and say, okay, if it's going to be, if a weaker acid is a stronger conjugate base, that means that like H2S would be, or S2 negative is going to be a stronger base because that H2S is stronger than H2SE. That's one way you could think about it. And the other way you could think about it, and the reason that the reason that acid is stronger is because Se2 or H2Se, in that molecule, Se is larger, and so that bond is weaker between the Se and the H's, and so the H is able to leave more easily. But for to consider it like in terms of which base is going to be stronger, you could think about it in terms of which is going to be able to hold on to that negative charge more easily and be more stable with it, or like which one is going to be like less able to hold on to that negative charge, in terms of thinking about it in terms of like acid strength again, because even though electronegativity increases as you go, did not mean to do that. As electronegativity, like even as electronegativity increases as you go, like this across the table, when you think about acids, electronegativity only matters as you go across the table, and then it matters, and then size matters more as you go down, even though the electronegativity trend is going up. And so in this case, because S is a smaller molecule, it wants the H more, it wants the H to be stable more than the Se does, because that's able to have a stronger bond with the H than the Se is able to. And so for both of those reasons, it's kind of the same thought process, just in terms of thinking about which is the stronger base versus which one is the stronger acid, and I'm kind of working backwards. But in either way you think about it, you should still get that S2 is the stronger base, or S2 minus is the stronger base. And then we have one where you had to rank the binary acids in terms of increasing acid strength. So I should open that periodic table back up. And so if you remember binary acids, there's two main trends that determine like the strength of an acid. The first one is electronegativity. And so as you move across the table, you want to consider electronegativity. So when you go across the period, and then you also want to consider that going down, you're going to get stronger acids because these molecules are getting bigger. So even though electronegativity goes across and up to increase, the difference between like when you compare two elements, the size is more important than the electronegativity when you go down a table, and so or down a period, and so or down a group. When you go down one of these columns, the size is more important than electronegativity. And so for these, you can compare sizes and stuff. So NaH is one of those where in this scenario, the electronegativity difference is such that in this case, the H actually acts as a base. It actually acts as a base because the Na is the one who's positively charged here, and the H is the one who's negatively charged. And so if you ever saw like NaH, LiH, KH, they would all be the same scenario where I think you probably would only ever see NaH and LiH. There where they act actually as bases instead of as acids, because that H is actually on a negative charge because that sodium wants to lose an electron so badly. And so that's going to be your weakest acid because it's actually a base. And then you have, so you can say, okay, this is my weakest acid. And then you only have one strong acid listed here. So your HI is your strongest acid. So you at least know when you do it in order of increasing acid strength that you need to have NaH first, and then you have these two, and then you have HI is your strongest acid. So now you still determine which one is stronger, H2TE or H2S. And so if you find this on the table here, we have H2TE is here and H2S is here. And because tellurium is so much bigger than sulfur, it makes it much easier. That bond is like much less strong because it's stretching so much wider to between the two nuclei, between the H and between the tellurium. And so because of that, this one is the stronger acid because the H can leave more easily with the larger molecule or with the larger atom. And so it would go NaH, H2S, H2TE, HI. Any questions on that one? Okay, so then for the next one here, we just have to identify the bronsted-lowry base and the conjugates. And so, or sorry, like the bronsted-lowry acid, the bronsted-lowry base, and the conjugates. And so we look to the left side of the equation to identify the acid, the base here. And so you know that water can act as either the acid or the base. So you have to determine if this CH3NH2 is an acid or a base. This is kind of a tricky one because you have H is bonded to a nitrogen, and that can be, like, you know that H is bonded to nitrogen can be acidic. But your hint here is that you're producing OH minus, and this is actually gaining an additional proton. And so because it's gaining an additional proton, we know that this is the base, and then this is going to act as the acid. So this is going to act as the proton donor, and the CH3 and H2 is going to act as the proton recipient. And so when you do the conjugates on this side, this will be the conjugate acid, and this will be the conjugate base. Because now CH3 NaH3 plus is acidic because now it has extra proton it can donate, and OH minus can take on another proton, so it's a base now. Hopefully that one was okay. And now we're getting further away from like acid strength and more into actually the calculations for acidity. So for the table here, you had to use the information in the table to fill in the rest of the information in the table. And so for the first one, you have to use, so first to find the pH, you can just do negative. So if you remember, pH equals negative log of H3O plus. And so in order to solve for the pH, you just do negative log of this value and you should get 2.5. And then to solve for the OH concentration, if you remember Kw, which is 1 equals 1 times 10 to the negative 14th, equals the concentration of the H3O plus times the concentration of OH minus. And so in order to solve for the concentration of OH minus, you would do 1 times 10 to the negative 14th divided by your concentration of H3O plus. And when you do that, you would get a concentration of 2.9 times 10 to the negative 12 for your molarity of OH minus. And then because your pH is less than 7, it is an acidic solution. For the second part of the problem, you are given the pH. So the one that's easiest to figure out first might be your acidic or basic column. And because it's above 7, it's basic. You just barely basic, but it is basic. And then when you do your calculations here, so you have your pH right now. And if you remember your pH, in order to get your H3O plus concentration, if you kind of undo this equation in order to isolate H3O plus, you would get H3O plus equals 10 to the negative pH. And so you just plug in 10 to the negative 7.15 and you get a concentration of 7.1 times 10 to the negative 8th molar of H3O plus. And then you use that Kw expression again. And so you would do Kw equals 1 times 10 to the negative 14th, and you would do and that equals the concentration of H3O plus times your concentration of OH minus. So to solve for your concentration of OH minus, you would do 1 times 10 to the negative 14th divided by 7.1 times 10 to the negative 8th, and you get a concentration of 1.4 times 10 to the negative 7th molar. Any questions about that one?
Yeah, I actually have a question.
Yeah.
For the OH concentration for number 1,
Yeah.
I did it a different way. So because I found out that the pH is 2.5, I just did 14 minus 2.5, and that's how I got 11.5 for the POH. And then I did like 10 to the negative 11.5 to get the OH, but I didn't get the same concentration. So I guess I just want to know like why it didn't work for that one, but I did the same thing for the OH on the bottom and I got that answer right.
All right, so if I do 14, so you got 11.5, and then 10. Because I got the same things as you. I got when I did 14 minus the pH, I got 11.5, and then I did 10 to the negative 11.5, which should give you the concentration of OH minus, but I got 3.16 times 10 to the negative 12.
Yeah, that's what I got too.
I guess like when you think about it, the difference between these two numbers is like really small because they have 11 zeros in front of them. But it still seems weird that you wouldn't get the same thing.
Yes, I didn't know like if I did something wrong or like.
No,
what.
I don't think you did anything wrong. I'm just kind of confused why that isn't working though. Maybe let me make sure that negative log of 3.5 e negative 3. This is 2.455. So maybe if we plug in instead of doing 2.5, maybe if we plug in 2.455, maybe it'll give us a better answer. So if you like actually do the negative log of 3.5 times 10 to the negative 3, and then you take that number, that entire number, and put it in, and then you do 14 minus that whole number, so it's like 2.455931956, and then if you do 10 to the negative 11.54406,804, then you get 2.857 times 10 to the negative 12. So it's just been a rounding error, or like a rounding confusion.
Okay.
So I don't think you really did anything wrong with that, but I guess like for these types of problems, try to keep as many sig figs as you can until the end.
Yeah, probably so.
Yeah, but that's all. But you, the thought process that you had there was like completely 100% correct.
Okay, okay. Yeah, because I did like the way you just said it, and now I'm getting the answer. Okay, so that makes sense.
Yeah, so it's just been a rounding thing, but the way you did it is totally correct.
Okay, thank you.
Uh-huh. Okay, so the next one, and that was a good question. I was like, at first I was like, wait, how did that happen?
Yeah.
For the next one, I think it's like kind of a weird question. It's about it tells that the value of kW increases with increasing temperature, and you have to figure out if it's endo or exothermic. So this one was on one of your previous exams, but I still think it's kind of a weird question to think about. And so you have to consider the value of kW increases with increasing temperature. So it's like, you know, what does that mean in terms of endo or exothermic? And so if you have the autoionization of water, if you remember, it's 2H2O goes to, and that's liquid water, goes to H3O plus OH minus, and both OH minus and H3O plus are aqueous. And so when you write your KW is H3O plus times OH minus. And so in order for your KW to increase with increasing temperature, it must mean that like when you increase the temperature, you're going to produce more H3O plus and OH minus because your KW would have to increase. And so you have to kind of figure out, okay, which side, if I add it onto and I increase it, will it produce more H3O plus and OH minus? So if you add it, if you're like, okay, I think it should be exothermic. If you put heat on this side, right? If you were to increase the heat on this side, if it were exothermic, you can think of the heat as a product. So if you increase the heat on this side, it would actually push the reaction in this direction towards the reactants, which means the KW would decrease because it would produce more of that water and these concentrations would decrease. But if you think of it as an exothermic or an endothermic reaction and you think of heat as a reactant, then in this case, if you increase the heat, it's like increasing one of the reactants, it's just going to push the reaction to the right. It's going to increase the concentration of H3O plus and OH minus, and this will give us a larger KW. So KW would increase with increasing temperature. And so because of that, the autoionization of water is endothermic. Any questions on that one? It's like kind of acid basis, but also kind of La Chatelier's principle. So then 13 was just identifying the bronsted-Lowry conjugate acid-base pair. So hopefully this wasn't too difficult. It would be NH3, NH4 plus. Conjugate acid-base. Yeah, so it would be this one. And then for which ion will be basic in aqueous solution, you have to consider which one is like which one would be like not bonded to a strong acid. And so if you consider like their conjugates here, HBr is a strong acid. So Br minus is just going to hang out in the solution. It's totally cool just being Br minus. It dissociates completely. That Br minus is able to hold on to that negative charge really well, and it's totally fine. And HBr is a strong acid. HNO3 is also a strong acid, and same with NO3. It can just hang out in the solution and be totally happy, and it's totally content. And then H2SO4 is also a strong acid, and so HSO4 minus, once it loses one of its protons, it's totally okay to hang out in the solution by itself after the first ionization. And so that will be that'll just be hanging out in the solution. It will not be basic. It'll actually be kind of acidic because it has another H that it could theoretically lose. And then finally, you have the SO3 2 minus. If you think about the conjugate of that, it would be H2SO3. H2SO3 is not one of your strong acids. And so that's the only one where after you lose both those protons, you're going to have SO3 2- and it's a weak acid. And so, or sorry, H2SO3 is a weak acid. And so because of that, SO3 2- will be a base. And so it'll make a basic solution. And so the answer would be D, SO3 2-. And then we have from the pH of a 0.175 molar NaCN solution, and you're given the Ka value for HCN. And so in order to solve this one, what you have is actually a Kb expression, because you have Cn minus plus H2O is going to yield HCN plus OH minus. And so this is a liquid, so it won't get put into your K expression, but you'll have your Kb is products of a reactant. So you'd produce HCN times OH minus over your Cn minus. And so the first thing to do here is, because we have a Kb, just solve for Kb here. So K, you remember Kb times Ka equals Kw. So in order to solve for our Kb, we just do 1 times 10 to the negative 14th divided by this Ka value. And so when we do that, we get a Kb equal to 2.04 times 10 to the negative 5th. And so we can plug everything. Okay, so first thing that we have is we're going to assume small x. So we're not going to put, we're just going to put 0.175 molar down here. We're not going to actually do 0.175 minus x. And then we know that we're going to produce X amount of HCN and also X amount of OH minus. And so I'm going to put X squared up top. And so to solve for, and here's our Kb. And so to solve for the X value, we do this Kb times 0.175. And then we square root it. And you'd get an X equal to 0.0019. And if you do the if you do like the check for percent ionization, it's still under 5%, so it's okay to use small x for. So we get an X value of 0.0019. We know that's our OH minus concentration, so we can do POH equals negative log of 0.0019, because it's our concentration of OH minus. And we get a POH value of 2.72. That's our POH, and we're looking for our pH. So because pH plus POH equals 14, we can do 14 minus 2.72 to get our pH. And when you do that, you should get 11.28. So the solution to this one was 11.28. Any questions on that one? All right. For this next one then, we have which compound will form an acidic solution when dissolved in water. So kind of the opposite of the one that we had earlier, where we're like, which is going to form an which one will be basic in aqueous solution. It's kind of the opposite, where it's like which one won't be acidic. And so we have to figure out what each of these is going to dissolve into. And so NH4Cl will dissolve into NH4 plus and Cl minus. But Cl minus is going to be HCl, would be the conjugate here. And if you notice, a strong acid. And so Cl minus is like totally cool hanging out in the solution by itself. It can hold on to that negative charge really well. And it's not going to try to, like, it already dissociated completely. So it's not going to try to bond to an H now. So it doesn't act basic. It just hangs out in the solution like a spectator. And so NH4 plus is acidic though. And so that'll form an acidic solution. For the rest of these, when you think about it, like Na plus would not have a charge on it because NaOH is a strong acid or a strong base, so that would just hang out. Same with KOH is a strong base, so it would just hang out, and then same with CaOH too. It would just, the Ca2 plus would just be fine hanging out in the solution by itself. So the NH4Cl is the only one that produces an acidic solution when dissolved in water. So it'll be A. Any questions about that? So then we have, what volume of 0.855 molar KOH solution do you need to make 3.55 liters of a solution with a pH of 12.4? And so the first thing you have to consider here is that it's asking for pH right now, but KOH is a strong base. So what you really want is the concentration of OH minus that'll create that pH. And so you can first solve for your target POH instead of pH because it'll make the comparison easier to the concentration of OH, KOH. And so when you do that, if you do 14 minus 12.4, you'll get a POH of 1.6. So then you can determine how many moles or how much molar OH minus you need in order to get a solution with a POH of 1.6. And so you do 10 to the negative POH and you get 0.025 molar OH minus. So that's your OH minus concentration. So now you're asking how many, like basically you need to equate the number of moles of OH minus that are in the solution with the number of moles of KOH in the solution here. And so in order to compare the two of these, we can do the M1V1 equals M2V2 expression. And so if you were to do this, you have your molarity 1 for OH is going to be 0.025. You have your volume is 3.55 liters. And then you have your concentration of KOH is 0.855 molar, and you're looking for that volume. So we can rewrite it as M1V1 over M2 in order to isolate that V2. And so if you substitute in the values for all of these, you'll get 0.104 liters of KOH. So in order to make a solution that is a pH of 12.4 and it is 3.55 liters, you would need to add in 0.104 liters of 0.855 molar KOH. Any questions on that one? All right, so earlier we ranked solutions in order of acidity, but now we're going to do it in order of increasing basicity. And so to figure out like how to rank these in terms of which is the strongest versus the weakest. And so first thing that we know here, that off the bat you can be like, okay, this one's going to be the strongest base is the KOH. And so KOH is a strong base, so that should be our strongest here. And then we have to start comparing the how strong these other ones are. And so KBr is just a salt because if you think about KOH is a strong base, so that K positive is totally okay to hang out in the solution. But HBr is also a strong acid. And so that Br minus is also able to just hang out in the solution. So KBr is literally minus, is literally is literally neutral. So we know that KBr is less than KOH. But then to go to the rest of this. So for the CH3 NH3 Br, when we dissolve this, Br minus is going to just hang out in the solution, not really doing anything because it's a neutral ion. But we're going to produce CH3 NH3 plus, which is actually acidic because it can donate one of those protons. And so because of that, instead of actually being basic, that one's actually acidic. So that's definitely going to be our least CH3 NH3Br. Okay, so now we have to figure out just the difference between KCN and then C5H5NHNO2. And so okay, so this solution has you do the full calculation for the basicity of it, but like for how much it'll dissolve. But if you compare KCN and C5H5 and HNO2, so C5H5 NHNO2 is sorry, C5H5 and HNO2 is the conjugate acid of the weak base C5H5NO2, and the anion is the weak base of HNO2. So it'll actually produce like a little bit of like a strong, oh, sorry, it'll produce like a little bit of a weak acid and a little bit of a weak base here. But KCN here is only going to produce a neutral ion and a base here. And so overall here, because this one's producing an acid as well, instead of just producing, because this part of this ion is going to be acidic here, but this part is basic. So however much NO2 is produced is going to kind of be like neutralized out by how this is acidic, and so the pH will kind of like be in between. Whereas the KCN, the K is just a neutral ion, it's only CN minus that's contributing here. And so because of that, your correct order is going to be CH3 NH3Br, which is positive, KBr, because it's entirely neutral, C5H5NH2, NHNO2, because it's producing a little bit of acid, but also a little bit of base, so it'll be a little bit basic. And then it's also producing KCN, which is just a weak base, and so that one will be the second strongest, and then KOH is the strong, or sorry, the only strong base, so it'll be your strongest base. And then when you go to this next problem, it's about calculating the concentrations of all the species in a 0.225 solution of this weak acid. And so in order to do this, you would need to do a Ka expression. So if you know that once C6H5NH3Cl dissolves, it'll produce C6H5NH3 plus, and then Cl minus is a conjugate of the strong acid, so it's going to kind of like hang out in the solution. And so this is the weak acid that you're working with here. And so if you're doing all the all the species in the or the concentrations of all the species in the solution, the Cl minus concentration, the Cl is just going to hang out in there, and so nothing will really happen to the Cl, so it'll just stay with the original concentration. So the concentration of Cl minus is 0.225 molar. But really, like, the calculation is the important part. You have to do the calculation for how much the C6H5NH3 plus is going to produce of the conjugate base, and also of H3O plus. And so the next one here, then we consider our Ka expression, just like how you would for any kind of weak acid. So because this is our weak acid here, we have that on the bottom. It's going to produce H3O plus. It'll also produce its conjugate base. And so when we plug in, we'll go for a small k approximation. And so we will assume 0.225 molar CH5 NH3Cl. And then in order to determine our Ka value, I guess the book provides you with your Kb value of C6H5NH2 as 3.9 times 10 to the negative 10. So the Ka value that you're working with here is 2.56 times 10 to the negative 5. And then you use that Ka value you just found to plug it into your Ka expression here, and you would get 2.56 times 10 to the negative 5th. And we can do the small x approximation to get x as 0.0024 molar. And so once we do, because we're going to end up having our x as that, we'd have the H3O plus concentration and the C6H5NH2 concentrations as 0.0024 molar at equilibrium. But in order to find our C6H5NH3 concentration, we have to kind of go back to our ice table and do the initial minus that change, because the x is our change. So if we do 0.225 minus that change, we would get a concentration of 0.226 molar. So the concentration of C6H5NH3 plus at equilibrium will be 0.226 molar. I don't think you'd ever get a question like this on one of the exams, honestly, but it's a good exercise to just do a weak acid calculation. And you have the exact same thing here, just in different species. And so for this, it's a weak diprotic acid. And so really the only important part is the dissolution of the first ion. And so at equilibrium, so to do an ice table here, and we have to just plug in our Ka expression. So you'd have your delta X is going to be okay. So first what happens is that because it's a strong acid, because H2SO, actually H2SO3 is a weak acid, so it would only produce 0.005 of this, and then we go minus X, and then you'd have plus X on either side here. And so it would do a small X approximation here, and then you could do or actually, because the Ka is small, you have to do the full quadratic formula for this one. And so if you were to solve the quadratic formula, which I don't think they're going to give you a quadratic formula on the exam either. But if you were to do the quadratic formula here, if you multiply this whole thing out, you get x squared minus 1.6x plus, or 1.6 times 10 to the negative second. And then you do times 0.5 minus x because of this value right here. And so when you solve for this x in the quadratic formula, you get 0.081 molar. I really don't think they're going to give you any quadratic formula tomorrow on the exam. But the more important one, I guess, is to do the small x approximation one, because I think there will be weak acid stuff on the exam. And so an important thing to remember here is that your ionization, you can go through the whole calculation for the weak acid dissolution of HSO3 for the second proton. But the thing is that, like, because this Ka is so small, it's going to produce such a small amount of additional SO3 that SO3 minus, that it's really almost negligible how much you're going to have in the solution. And the actual amount that's going to be like this X value is going to be 6.4 times 10 to the negative 8. And so this, which is also your Ka2. And so when you have this thing set up for the second proton lost in a diprotic acid, your X value is always equal to your Ka2 for the second proton. And so in order to see if it's even going to be like necessary, you can see, okay, if I add 6.4 times 10 to the negative 8 to 0.081, is it going to be like, is it going to change anything? And it definitely will not, because of how many sig figs you have. And so you would only get an H3O plus concentration of 0.081 molar, but because your X is still equal to your Ka2, you know that your SO32 minus concentration is going to be 6.4 times 10 to the -8. And I really would not expect them to put on a quadratic formula onto your exam. I said I can't promise it, but I really don't think they would. But the important thing I think to pull away from this problem is that if you ever got a question about the second like ionization of a diprotic acid or the third of a triprotic acid, your X value is always going to be equal to your Ka2. So for the second proton loss, for a weak diprotic acid, your second or your X value is always going to be equal to your Ka2. And so if it ever asked you, like it could literally just give you this and say like, how much SO32 negative will be formed if your Ka value for this, for H2SO3 is 6.4 times 10 to the -8. Then right off the top of your head, you can say it would be 6.4 times 10 to the -8 because that's a product you would get after the second ionization. Okay, so now we have another one about like more about like salts and acidity and basicity. So we're kind of moving into solubility here, but this one kind of is like the segue between solubility and acidity. And so you have which compound is more soluble in an acidic solution than in a neutral solution. So you need to consider which ion is going to be basic, because in a basic solution or in a water solution, you already have OH minus. And so if you're producing a weak base, it's going to go through the ionization and produce OH minus and cause the common ion effect. And so a molecule that does not have, or a molecule that has a basic ion that produces a basic solution is going to be more acidic or more soluble in an acidic solution because there's less of a common ion effect than in a neutral solution or in a basic solution. So PbBr2, because the Br2 is from HBr, which is a strong acid, your Br minus is only neutral. Same thing with CuCl. HCl is a strong acid, so your Cl minus is just going to be neutral. And then same with AgI, you'd produce HI, which is a strong acid. And so it would not, it would just be neutral in the solution, I minus. BAF2, on the other hand, would produce HF, and HF is a weak acid. And so because of that, F minus is going to be a weak base in your solution here. And because of that, the common ion effect, it'll actually be more soluble in an acidic solution than it would be in a neutral solution. Okay. So this next, now we're going into buffers here. And so it's like which combination of these species will be the best choice to make a buffer with a pH of 9.0. And so for this one here, you have to consider, so a buffer solution is going to be, you'd have pH equals pKa plus log base over acid. And so in order to, like, when this is like, which is the best choice for a pH of 9.0, that means that you want the pKa to be as close to 9.0 as possible. So I haven't looked at what you guys submitted here, but I think this one is kind of a tricky one because you might off the bat know this, that, okay, I want my pKa to be close to my pH. And you might think, oh, this one has a pKb of 8.76. That's great. I'll go with that one. But the thing is that that's your pKb. And so your pKa of the solution is actually 14 minus that. So if you did 14 minus 8.76, you'd actually get a Ka value, a pKa value of 5.24. And so that's way lower than what you're anticipating here. So then you can convert this one also into a pKa here. And so you do 14 minus 4.74 or 4.75, and you get 9.25 as your pKa value. And so with this information, now with it all in your pKa's, you can compare all these Ka's to which is the closest to the pH here. And that is A, which is the NH3 NH4Cl. Any questions on that one? Okay, the next one is just a common ion effect problem. And so it asks in which solution does HNO2 ionize less than it does in pure water. And the answer is D. And the reason for that is because this is going to dissolve and it's going to produce, like this is too long explanation, but basically the only thing here is that the NaNO2 is going to produce NO2 minus. There's going to be a common ion effect because HNO2 is also going to produce NO2 minus. And so it's going to dissolve less because in order to reach its K, it should dissociate less since NO2 minus is already present in the solution. And so because of that, it'll dissociate the least in NaNO2 than it does in pure water. So now the next one that we have is a buffer solution. So we have a solution contains 10 grams of HC2, H3O2, and 10 grams of NaC2, H3O2. And you have 150 milliliters of solution here. And so the first thing you have to do here is just get everything into molarities before you can plug it into your Henderson-Hasselbalch, because it is a weak acid, weak base solution, or it's a weak acid and its conjugate base. And so it'll be a buffer. And so what you can do is you can calculate the molarity of each of these. And so you divide by the molar mass of both of them, you'll get 0.16 molar of HC2NH3O2. And you can do the exact same thing for NaC2H3O2, get it in terms of moles. And then you can plug it into, or to figure out molarity first, because you're told it's 0.15 or 1.5. No, it's 150 milliliters of solution. So it'll be 0.15 liters. So you can divide your moles by 0.15 liters and get that you have a 1.1 molar solution of C5H5NH2 and a 0.813 molar solution of NaC2H3O2. And so now with this information, we can just plug into our Henderson-Hasselbalch using, we'll have to do negative log of 1.8 times 10 to the negative fifth, which is the Ka value for acetic acid. And you do log of base over acid. And your base here again is going to be the C2H3O2 minus, because it's the conjugate of your HC2H3O2. So once you do this, you should get 4.7 or negative, or no, it'll be positive because it's negative from here. It'll be 4.75 plus log of 0.813 over 1.11, which are the molarities that we saw for earlier. And then we would get a buffer of with a pH of 4.61. For this next one here, we use like Henderson-Hasselbalch, but kind of in a backwards fashion. So we're looking for the mass of sodium benzoate. You should add to 150 milliliters of a benzoic acid solution in order to get a buffer with a pH of 4.25. So you know the pH already here. We just need to figure out what the ratio should be in order to figure out how much sodium benzoate you should be adding in. And so if you do, okay, so they actually, instead of doing, because you'd add these two up anyway, and you're seeing no volume change, you could just get the molarity of the benzoic acid off the bat because you already have the molarity and the volume of it, and you can plug it into Henderson-Hasselbalch without having to solve for without having to go back later and do the volume. So we can just do the volume now instead, because the volume would cancel out in this expression anyhow. So if you do molarity times volume, you'll just get moles. And so you'll get 0.0225 moles of the acid, the benzoic acid. You can plug it into your Henderson-Hasselbalch equation, and you'll get that 0.05 equals log of this. You remember that the only way to undo a log, this isn't a natural log, this is a log, and so this is a log base of 10. So you just remember how it's like, in order to undo, like to solve for H3O plus concentration after you have POH, how you do 10 to the negative pH. It's the same thing here. So you do 10 like, to undo the log it is. I mean, so you do 10 to the 0.05, and then you do, if you do this, it'll undo the log and just give you the number of moles of salt over 0.0225, which is your moles of acid. And so you get 0.0225 times 10 to the negative second for the moles of salt. But it's not asking you for the moles of sodium benzoate, it's asking you for the mass. So you have it in terms of moles right now, you just multiply by the molar mass in order to get it into grams. So once you multiply it by 144.11 grams per mole, you would get 3.64 grams of sodium benzoate. So then we have to figure out the initial and final pH of a solution after adding in hydrochloric acid. And so you just have to do, in order to figure out the initial concentration or the initial pH of this, you would just do a Henderson-Hasselbalch, just like a classic Henderson-Hasselbalch. So you would just do like pKa plus log of base over acid. And so you're given those concentrations already. So it'll just be like pKa, so it'd be negative log of 1.8 times 10 to the negative fifth plus log of base over acid. So it would be your 0.115 molar over your 0.125. And you would get a pH of initial pH of 4.7. But then the trickier part is once you add in the HCl. And so for this, you would need to do a BCA table. And so initially, you do not have any so I don't know why it doesn't have it. So this would be 0.010. So you're adding in 0.010 moles of HCl. So before you can plug into this table here, the reason why they got these values are they just multiplied the volume times the concentration. So how it's 0.115 molar NaC2H3O2 times the liters. And so they did that for both of them in order to get the moles. So you can compare moles to moles because we only have moles of HCl, not volume. And so when we do this, we would get 0.0575 moles of sodium acetate and 0.0625 moles of acetic acid. Now, because we're adding in an acid here, it's going to react with the base in order to neutralize the solution. And so you want the base to be the one that's reacting with the acid here. And so in this solution, oh, sorry, it should be 0.01. In this equation here, you would do minus 0.010 because that's the limiting reactant, because this one has more, because it's 0.05. And so you would subtract minus 0.01, and you would get a zero concentration of H0 plus, a constant or a number of moles of 0.0475 of your conjugate acid or of your conjugate base, and then you would get 0.0725 moles of your acid. And we can plug back into Henderson-Hasselbalch, and you wouldn't have to do the liters again, because if you have the same number of liters here, when you do a ratio, they're going to cancel out anyhow. And so because of that, you could just plug the number of moles in. And so then after the addition of your HCl, your pH would be 4.56. And as a little check in your head, you can be like, okay, the initial pH was 4.70. Because I'm adding in HCl, that should reduce the pH because it's a strong acid. And so this pH after the addition of 0.01 moles of HCl should be lower than my initial pH, and it is. So that's kind of like a quick check you can do in your head just to make sure that you did everything correct. So this one was like I threw a titration one on here, but I know that it was probably so much to try to get through. really quick, like when you have a timer on the exam. I think this is probably way more than will actually be on your exam tomorrow. So I think if you had enough time to get through all of this, then you should be in really good shape for your like for timing, at least for your exam tomorrow. Because I think this is a ton of questions. And so for this one, we have a titration. So first asks you for the initial pH. And you're given a 20 milliliter solution of 0.105 H2O2. And so that's just a weak acid calculation. So the weak acid's going to ionize here. You would produce C2H3O2 minus and H3O plus. And so that would be your X. You're going to do a small X approximation here. And you would get an X equal to 0.00137 molar. And so that would be your H3O plus concentration once you do the calculation here. And if you plug it into a pH expression, you would get a pH equals negative log of H3O plus. And so you would get a pH of 2.86. And so the initial pH here would be 2.86. That's just your initial pH is just a classic like Ka weak acid calculation. For the volume of added base to get to the equivalent point for part 2 here, you would do your molarity times your volume. And so you have M1V1 equals M2V2. So you have your concentration of your analyte. So I guess like in order to be at the equivalence point, your moles of your acid have to equal your moles of your base. You know your moles of your acid already, and you have the concentration of your base. And so you need to find out the mole or the number of moles of your acid that are present, and then you know how many moles of your base you need to have. And then you have your concentration, and you can just solve for volume. So when you do M1V1 equals M2V2, it's saying number of moles need to be equal on each side. And so you would do 0.015, the concentration of your acid, times the volume of your acid, divided by the concentration of your base, and you would get 16.8 milliliters to reach the equivalence point. Then you have to find the pH at 5 milliliters of added base. So this is a BCA table. And so 5 milliliters of added base are going to be, is going to be 6.25 times 10 to the negative third when you do the concentration times the volume here. So that's how many moles you have of NaOH. So when you plug it into your equation here or into your table here, the NaOH is going to be the limiting reactant because it's so much smaller than the HC2H3O2. So you can subtract and get that 0 NaOH will be left. And then you would be producing 6.25 times 10 to the negative 3 of NaC2H3O2. And you'd be producing that's the number of moles of H2O as well. That's really important because H2O doesn't go into anything anyway. But for your new concentration of HC2H3O2, because you just use some of this HC2H3O2 to create NaC2 H3O2 and H2O minus, or sorry, H2O, you have to subtract how much you just used of it. And so your new volume of, or your new number of moles of HC2H3O2 would be 1.475 times 10 to the negative 3 after you subtract. And so now you can just plug into Henderson-Hasselbalch because you have your weak acid and your conjugate base. And so you can plug it into Henderson-Hasselbalch. And so just make sure you do base over acid and you get a pH of 4.37. Again, you can kind of do a mental check where your initial pH was 2.86. You're adding in a strong base, so the pH should be increasing. And so this, your pH did increase. Now your pH is up to 4.37. So your pH at 1/2 the equivalence point, pH just equals pKa here. And so at the halfway equivalence point, your pH equals your pKa, and your pKa is 4.74. Now we have the equivalence point, which I think is the most the hardest part of the problem. When you do your pH at your equivalence point, all of the moles of your conjugate or of your acid that you've had are going to react with that base to only form your conjugate base, because it's been entirely neutralized. You use up all of that strong base. But by using up all the strong base to neutralize it, you also use up all of your weak acid. So all you have left is your conjugate base. And so in order to solve for the concentration of OH minus to solve for your pH, you have to do like a classic KB calculation with just the concentration of your C2H3O2 minus. And so when you do like the classic KB expression here, where you would do first, because you are given your Ka is 1.8 times 10 to the negative fifth, you'd solve for KB as 5.6 times 10 to the negative 10th. And then you could do a small x approximation here, do x squared over 0.0571. And when you solve for your x, you get 5.6 times 10 to the negative 6 molar. And so your x is equal to your OH minus concentration. So in order to get your H3O plus concentration, you need to do your Kw divided by your OH concentration. And when you do that, you get 1.77 times 10 to the negative 9th. So finally, to finish off and to solve for the pH, you would do negative log of H3O plus, which is your 1.77 times 10 to the negative 9th, and you would get a pH of 8.75. The only thing that I didn't say that I think is important here is that you need to get in order to get your concentration here, you have to consider not only the volume from the analyte, the 20 milliliters here, but you also have to consider how much base you had to add in order to reach the equivalence point. So we already found that in part 2, but it was that 16.8. So that's where your new volume comes from. And then you divide your number of moles of your weak base by that new volume, and you would get 0.0571. And then finally, for adding 5 milliliters past the equivalence point, we just found the volume at the equivalence point was 36.8 milliliters. And so your volume at the 5 milliliters after the equivalence point is going to be will be 33.8 plus 5 milliliters, or so it would be 0.5 milliliters, and so that would give you 8.8 milliliters. And let me just make sure that's correct with what we had. Oh, sorry, it was 36.8. So So 36.8 plus 5 would be 41.8 milliliters. And so you could just do your number of moles of OH minus, because you've already neutralized everything at this point. And so in order to figure out the contribution just from your OH minus here, past the equivalence point, you would do your concentration of your OH minus, which is 0.135 times 0.005. You would get 6.75 times 10 to the negative fourth. And so you do 6.75 times 10 to the negative fourth divided by 4 which is your number of moles of OH minus. Oh, sorry, it's not 135, it's 125. So then instead of being 6.75, it would be 6.25. So you'd have 6.25 times 10⁴ moles of OH minus. You have your volume here, just in milliliters, so to convert it to liters. So you'd have 0.0418 liters. And so you could do 6.25 divided by 0.0418 liters, and you would get a new concentration of OH minus as 0.0149. So to solve for your H3O plus concentration, you can do the autoionization of water, 1.0 times 10⁻14 divided by that concentration, or by that concentration, 0.0149, which is your OH minus concentration. You get 6.7 times 10⁻13. And then you do negative log of this H3O plus concentration, you get 12.17. And this should make sense because at this point, your solution's been entirely neutralized. It's only base, and you have a ton of strong base in there. So it should be a really basic solution, which it is at 12.17. Okay, so now we're kind of out of the like acid base stuff and onto like entropy and delta G. And so for this question here, we have to predict at 1 temperature the reaction is spontaneous, but we're already given our delta H. And so the reaction that we're going to be using here is delta G equals delta H minus T delta S. So for the first one, we're already told our delta H is negative. Our delta S, we're going from 3 moles of gas on this side to 2 moles of gas on this side. So our S is negative as well. But that actually means that we would need to keep this term really small because it will turn positive, and delta G is only spontaneous when negative. And so we would need to keep this term really small in order to make sure that our delta G was still spontaneous, so that we didn't cancel out this negative value and make it positive. And so this would only be spontaneous at low temperatures for the first one. For the second one, our delta H is positive, but we're going from 2 moles of gas to 3 moles of gas, so our delta S is positive. And so we need to make this term really large in order to cancel out the positive value from delta H and make this all negative to make it spontaneous. So it's be spontaneous at high temperatures. And then for the next one, we have a negative delta H, and then we are going from 3 moles of gas to 2 moles of gas. The delta S is negative. It's the exact same scenario as in the first case, as in case A. And so again, in order to keep this term pretty small to not cancel out the negativity here, our delta S, since our delta S is negative, our temperature needs to be low in order to make that term pretty small. And so it's only spontaneous at low temperatures. And then finally, for the last one here, we have a delta H that's positive, and then we're going from 1 mole of gas to 1 mole of gas and 1 solid. So it's actually becoming less, the entropy is decreasing, so it's going to be negative, because as you go to the other side, you're also producing a solid, which is way more ordered. And then you compare CO2 to O2, there's way more complexity in CO2 than there is in O2. And so because of that, no matter what the temperature is, you're always going to get a positive delta G value, so it will never be spontaneous. So it's spontaneous at no temperatures for 4. Or for B. Oh my God, for D, not for 4 or D. I'm not sure how it's labeled. For this next one, we need to calculate delta S surroundings at 77 K for a reaction that has a delta H of negative 385 kilojoules. And so if you remember this this equation, it's delta S surroundings equals delta H reaction over T. The only thing you have to do here is just plug in your delta H reaction and your temperature. And so you do negative 385 kilojoules over 77 Kelvin, and you get 5 times 10 to the 3 joules per Kelvin. So your entropy change of the surroundings is 5.0 times 10 to the 3rd joules per Kelvin. For 31 here, we have to calculate for delta S universe. And so delta S universe is the delta S of the reaction plus the delta S of the surroundings. And so we have the delta S of the reaction, we need to figure out the S of surroundings. And we calculate just like how we calculated from the previous problem. So you would do delta S surroundings equals delta H reaction over temperature. And so you would do your negative, you do positive 115 kilojoules, but there's a negative sign in front of this reaction, so it would be negative 115 over 298 Kelvin. The only that's notable here is that this is in kilojoules, but usually delta S reaction is measured in joules, and like this one's measured in joules. So if you just multiply by 1,000, it'll give you the answer in joules. So you'll get negative 386 joules per Kelvin for the delta S of the surroundings. But you need to go one step further and just add delta S system with delta S surroundings, and you'll get a delta S of universe of negative 649 joules per Kelvin. And so this reaction would be like super spontaneous because since the entropy of the universe is, it would be super non-spontaneous because the delta S of the universe is really negative, which would mean that delta G was really positive and would give you a non-spontaneous reaction because the universe is actually getting more ordered from this reaction. So this one we have to calculate the free energy change at 25 degrees Celsius. We can just use our delta G equals delta H minus T delta S equation again. And so the thing to do here is that we're given our temperature in 25 degrees Celsius, so just make sure that you convert that to Kelvin. And so you would get 298 Kelvin. And so you would do the delta H minus temperature times your delta S, and just make sure that you're converting your delta S into kilojoules because your delta H is in kilojoules already. So you just need to make sure you have your common, you have to have the common label. And so you'll get negative 1,161 kilojoules, which is less than 0. It's negative, and so the reaction will be spontaneous. Any questions? Okay. All right. So we are at what is the molar entropy, or how does the molar entropy of a substance change with increasing temperature? Because as temperature increases, the particles are going to obtain more energy, and you'll have like some more more random behavior because they're able to have like more electron movement and everything. You're going to be able to have those electrons in additional microstates that are like more highly charged and everything. And so because of that, your molar entropy of a substance will increase as temperature increases. For this one, we have to determine the one that has the higher molar standard entropy. And so for NaNO3 solid versus NaNO3 aqueous, we would choose aqueous because it has water in the solution as well. So that makes it more complex. It also has those interactions with water. So NaNO3 aqueous would be the answer for A. For B, it would be the liquid because of the phase here. Because of the phase. So the liquid phase is going to be a higher entropy than the liquid phase will be a higher entropy than the gas because it's a liquid, so it has more movement than, I messed up. It'll be the gas because the gas has a higher energy phase, and so because of that, the entropy of a gas will be a higher entropy than of a liquid, and so it'll be Br2 gas. For the next one, we have Br2 versus F2. Br2 is larger than F2. It's lower on the periodic table and also has the larger molar mass. And because of that, it would be Br2 that was had the higher molar standard molar entropy. So it would be Br2 again. And then for this next one, this molecule is way more complex than SO2 because it has so much more interactions of carbons and hydrogens and such a long carbon chain. And so because of that, there's way more complexity in D than there is in or sorry, not in D. In D, there's way more complexity in this CH3, CH2, CH2, CH3 molecule than there is in SO2. And the same thing follows for CH4 versus CH3, CH3. This molecule is way more complex than this molecule. And so this one has more complexity and has a greater standard molar entropy. This next one, we're ranking these substances in order of increasing molar standard entropy. And so in order to do this, first thing we can say is that H is the only one that contains, or I guess like first, we compare H and HE and NE because they're the only ones that only contain one atom. HE has the longest or has the smallest, smaller mass out of the two of them. And so that is the, that one has the least standard molar entropy. Next up is neon because it's only one single atom. Then we compare NH3 and SO2. Because SO2 has 3 atoms and NH3 has 4 atoms, NH3 is much more complex than SO2. And so because of that, SO2 is the next, has the next increasing standard molar entropy. And NH3 is next because that's 4, whereas this one has 1, 4, 5, 7, 8, 9. So this one has 9 total atoms in it. So that's definitely the most complex molecule here. And so the actual order is HE is less than NE, is less than SO2, is less than NH3, is less than CH3, CH2, OH. Then we have to determine delta H for the reaction, or delta G for the reaction. We're given 2 different reactions here. And the one that we have to change here is that we need to flip this reaction around because Fe in our target equation, Fe2O3 is on the other side. And so we're going to flip this around and make this positive. And then the other part of this is that we have 3 halves O2 up here, and we have which we need to cancel out. And we have 3 CO and 3 CO2 in the equation here. And so this one needs to be multiplied by 3. So it's literally just Hess's law. And so once you do those calculations, you would get a delta G value of negative 29.4 kilojoules. For the next reaction, you have you have to calculate the delta G under the following conditions, and you're given the pressures for all of these substances. And so to figure out the delta G value, we have to use this equation, the delta G equals delta G standard plus RT ln Q. And so the first thing that we can do is we can figure out so actually, was it not given to you? So what should have been given to you here is that the standard molar entropy, sorry guys, the standard molar entropy of formation for this is 25.1 kilojoules. Sorry, that should have been included. So then what you have to do is actually just calculate your Q value. And so in order to calculate Q, you do products over reactants. And just remember your coefficient in front of the 2H2. And you can just plug the pressures in and you would get a QP of 0.004896. And so you can just plug this into delta G plus RT ln Q. The only thing to make sure is that you convert your temperature into Kelvin and you are using the correct R, because this R value is for, because like we're working with joules and stuff, working with energy here, you want to be using the 8.3141. The other thing is that because we're going to do everything in kilojoules right now, because this is kilojoules, because your standard delta G is given in kilojoules, you'd have to make sure that you converted this into kilojoules as well. The other option you could do is just convert this into joules and then add them up together. And then you would just plug your Q value in. So you do the delta G equals delta G plus RT ln Q. And so you would get 11.9 kilojoules as your 11.9 kilojoules as your standard, not as your standard, as your delta G for this reaction here. So now for this one, you have to do everything. So for this one, you have to do 3 different conditions. You have standard conditions, equilibrium, and with different pressures. And so in order to calculate the delta G for this reaction here, at standard conditions, you know that your Q is going to equal 1 because you do 1 times, it'd be like 1 over 1 times 1 squared. So it would just be 1 for your Q value. And so your delta G is just going to equal your delta G standard. And so your delta G of your reaction here will just be negative RT ln of Q because it's your delta G standard. And so since delta G standard equals this, you can just plug in your K value. And so your K value is 2.26 times 10 to the 4th. So you just plug that in here and you make sure that you're using the right constant, and you would get negative 24,839.4 joules per mole. If you convert that into kilojoules, it would be negative 24.84 kilojoules per mole. And so that would be your delta G of reaction. And a reminder again, you have the equations like delta G reaction equals negative RT ln K. But because at your standard conditions here, you would do delta G reaction, or sorry, you did delta G reaction equals your standard delta G, so delta G standard plus RT ln Q. But when your Q is 1, this whole thing goes to 0, this whole term. And so you just have delta G reaction equals delta G standard. And so now your delta G reaction equals your delta G standard. So you can plug in your delta G reaction into this equation now under standard conditions. And so for standard conditions, then you get a delta G value of negative 24.84 kilojoules per mole. Okay, so now you have your standard conditions. So you have your delta G standard. So now at equilibrium, you have Q equals Kp, and you know delta G reaction equals delta G of standard plus RT ln of K. You already just solved for your delta G standard because what you were just doing was your delta G under standard conditions, so that 24.84. So you plug that in here, and then you would do your RT ln K again. And again, just make sure you're using the right R and the right temperature, and you can bring it to Kelvin. Once you do it, you end up just getting negative 24,840 plus 24,840, which they're going to cancel out and equal 0. So at equilibrium, delta G of reaction is 0. So you can also just remember that at equilibrium, delta G of reaction is equal to 0, but that's like the full calculation for where that is. And then we also have under these conditions, so our Q value would be based on the equation. And so because you have the coefficient of 2 in front of H2, make sure you're squaring that value. But you're given all of your pressures here. So we can just plug them in and get a Q value of 1 million, I think. And so you just plug it into delta G equals delta G standard plus RT ln of Q. Remember, you solve for your delta G standard in the first part of the equation here with the 24,830, 139. And then you can just do RT ln Q, and your Q in this case is 1 million. And so you'll end up getting 9.39 kilojoules per mole for the delta G. Okay, so you have 2 left here. So to figure out the redox reaction of this, your first step is to break this into 2 half reactions to figure out what's being oxidized and what's being reduced. And so the way we can do this is that your, so here, your BrO3, because the oxygens are each going to have a -2 oxidation number, this is carrying a total oxidation number of -6, but you do have the one negative charge in the total atom. And so our Br is holding a charge of +5 for oxidation. And then over here, it's going to -1, so that's being oxidized. And then your N2 gas is going to have a charge of 0 or oxidation of 0 on it. And over here, because, so this is being reduced. I said oxidized, but it's going from from +5 to -1, so it's being reduced. And then your N2H4 is going from having, the H4 would have an oxidation of +4 because each of those H's is an oxidation number of +1. And so in order to balance it out, then each of these nitrogens, in total, they're carrying -4, but each of the nitrogens is carrying -2. So now it's going from -2 on each nitrogen to 0 on each nitrogen. And so the oxidation is N2H4 goes to N2, and then our reduction is BrO3 negative goes to Br minus. Okay, but this is clearly not totally balanced because we are missing our hydrogens and our oxygens here. And so it's to add those in, but we're working within an acidic solution. So even though we can add in our, like H plus for the NH4 here, we can't just add in like 3 oxygens here. So we add in 3 H2O, but when we add in 3 H2O, we have 6 new hydrogens to account for. So we add in 6 H plus here. Then we have to make sure that our electrons are correct here. And so here we have, on this side of the equation, we have a charge of 0. But on this side of the equation, coming from the 4 hydrogens, they each have a charge of +1. So we need 4 electrons to balance them out. And then for reduction, we have, because we have 6 hydrogens on this side, because of the 3 H2O that we had to add, we're going to add 6 electrons in order to cancel out the positive charge from these 6 protons. And so in order to really combine these equations, we need to have the same number of electrons on either side. So our lowest common multiple is 12. So we multiplied this equation by 3. And we multiplied this equation by 2. And so then we get this expression. So we get 2BrO3 plus 12H plus 12E negative yields 2Br minus plus 6 H2O. And then we have 3 N2H4 plus, or sorry, yields 3 N2 plus 12H plus 12E. Our electrons cancel. And actually our H pluses cancel as well. And so all we're left with is just 2BrO3 plus 3 N2H4 yields 2Br minus plus 3 N2, and then the 6 H2O account for the hydrogens and the oxygens. For our last question here, we have we have 2 more questions. We have calculate delta G at 25 degrees Celsius for this reaction here. So the first thing we have to do is convert to we have to figure out what our anode and our cathode is in order to find our delta G, not our delta G, our E cell. And so we can just convert it. So we can figure out which one is being oxidized, which one's being reduced. So because this one has the lower voltage, we want to make this the anode. It's more likely to be reduced, and so, or more likely to be oxidized. And so we're going to go 2Br minus yields Br2 plus 2E negative. And so it'll be negative 1.09. So when we figure out E cell, we're going to add these 2 up to have E standard reduction and E standard oxidation. And when we add these 2 up, we will get a value of negative Oh, okay. Because, sorry, I made a mistake here. Because in this reaction, we're actually already told which one is oxidized, which one is reduced. So the Br2 is being reduced and the Cl2 is being oxidized. And so because the Cl2 is being oxidized, even though it's not conducive, it would be negative 1.36 because it's being oxidized since we're given the chemical equation here. So to figure out our E of reaction, we would add these two values up. So we would do negative 1.36 plus positive 1.09. And then you'd have a E standard of negative 0.27 volts. And then I could use negative N times Faraday's constant times E cell. So we have E cell. We can look at this equation and just determine, since we're already given the half cells here, we know that this is only going to it's only going to like use up 2 moles of electrons. And so N equals 2, and then Faraday's constant is 96,485. So when we just multiply up all of these values, we'll end up getting 52 kilojoules. And so our delta G of our reaction is 52 kilojoules, which is non-spontaneous. You kind of check yourself, so your delta G is positive. And so because your delta G is positive, our E cell should be negative, and it is because we have negative 0.27 as our E cell. Finally, for the last question, we have to calculate the cell potential at 25 degrees Celsius under each set of conditions. And so we have standard conditions first. And so under standard conditions, our Q is going to equal 1. And so when Q equals 1 here, then we just have to do so usually we have E cell we're calculating for a cell potential here, so we're actually calculating E. And so we would use the E cell equals our E standard times our minus voltage divided by N times log of Q. Because our Q for standard conditions is 1 here, we can just plug it in, so this whole term is going to go to 0. And so our E cell actually just equals our E standard, which is just 2.334. And the way that that's calculated is using the chart of like half reactions. I don't think you'd ever have to refer to the textbook while you're taking an exam, so they probably would give you the half reactions that they did up here. But if you were to solve for the half, like the voltage from E cell, like for E standard, it would be 2.334. And then for the reaction quotient, we would have Mg2 plus cubed, because for our reaction here, we have 3 magnesiums, or we only have 2 irons. And so you only incorporate the aqueous ones into the Q expression because solids do not get put into equilibrium expressions. And so you would do 2.51 molar divided by 2.5 molar cubed divided by 1 times 10 to the -3 molar squared. And so you get a Q value of 1.56 times 1.5625 times 10 to the 7th. And you would plug it into the same expression as above. And so you would get 2.263 as your voltage. And then you have the last one here. We have to do a Q again, we just do the exact same thing here, except we have different values for our Q and our F. And so instead, now when we get our Q value, it's 8.4375 times 10 to the -10. And then we would plug it into the same equation that we've been using, and we would get an E cell of 2.423 volts. And so our cell potential under standard conditions, or under these last conditions, would be 2.423. All right. That's the whole mock exam. If you guys have any last questions, I can definitely answer them, but otherwise you're totally free to go. And good luck on your exam tomorrow. I'm sure you guys will all do amazing.
Oh, I don't know if you can hear me.
Yeah, I can hear you. Sorry.
Let me know if you can.
Did you have a question?
I did a mock exam and there was a question asking for like the redox reaction in a basic solution.
Yeah.
I was wondering if we could go over that real quickly.
Yeah.
Because,
Do you have the problem by any chance?
I should.
Okay, I can also just pull up a random one for in the basic solution if you'd rather.
Because I felt like I got it, like I was confident about it, but then I'm like, oh damn, like
Really?
it
You got
wasn't
it wrong?
it. Mm-hmm.
Huh. I feel like some of these, like they also should be programmed wrong, some of them too. So I'm not sure to see.
Do you want me to show my screen?
Yeah, if you're okay with that, that would be awesome.
Okay, yes, we can do that. It's loading.
Okay, sounds good.
Can you see it?
Yeah, I can see it. Okay, so this one. All right.
The part that confused me was like right here when they were balancing, they wrote down +4 HO minus, and I was like, wait, we don't even do that.
Yeah, okay, let's do it. So okay, so the reason that they have 4 OH there is because they're accounting for, okay, so yeah, why do they do 4 OH instead of 2 OH?
They did the 2H2O here, and I was like, okay, yeah, like, but I would have thought they would have done like the 2H2O on the reactant side because it's the one that is missing the oxygens.
So because it's basic, you have to have, like, you add the OH instead of adding H2O. So when you add like oxygen to one side, you add OH instead of adding water in a basic solution instead. So that's why they added the OH to that side. So let's see. So I'm just kind of confused why they added 4 OH instead of 2. Okay, so it would be, so it's ALS going to AlO2. So when I'm like thinking about how to do this, I'd be like, okay, you add 2 OHs to the left side to balance out the oxygens. And if you add the 2 OHs, okay, so I think the reason for it, I think, is because they have to add those oxygens, but you can't add the oxygens in by themselves. So like you can't just add like oxygen gas in there. So you have to make up for the oxygen. So you would add in like 2 OH, for example. So you'd add in like, if you add like 2 OH to the left side first, okay? So it's like, okay, I'm going to add 2 OH in here, but then you can't add in H plus because then you'd have, like that would be like in an acidic solution. So you can't do that. So because you can't add protons in by themselves, you can't do that. So then when you add in, so it's like you basically need to have enough hydroxides where you're still creating some oxygens from the H2O, but you're not, like you don't have any protons by themselves. Does that make sense? And so when you,
Okay.
so what they're really doing here is that they go to add the OH to balance in the oxygens here because it's in a basic solution. If you go and you add in 2 OHs and you try to balance out on the other side and you add in an H2O, you just added in another oxygen. So then it's not balanced anymore because you still don't have that equal on the other side. So the only way to make it equal is to do the two H2O on the right side and the 4 OH on the left side, so that you can still have, like you'd have 4 hydrogens and 4 oxygens on either side. Does that make sense?
Yeah.
So that's why I did that.
Okay. And this only applies if you like doing for basic solutions, right?
Yeah, because if we were doing this, if we were to balance this in acidic, we would be like, okay, let's just add 2 H2O to the left side of the equation, and then we would just add 4 H plus to the right side of the equation. But because it's basic, we have to add in hydroxide instead.
Okay. I
Okay.
think I know.
Okay.
Okay. Yeah, that was like my question for why adding
That's a good question. If you guys are good though, you're totally free to go. If you have any other questions, I'm happy to answer. But if not, you're totally free to go. And then if you're like studying any more tonight and you come across any questions, if you shoot me an email, I can definitely respond to it and help you with whatever questions you might have. Oh, you know how you asked me a question last week about the one problem? They never replied to my email, but I found the one solution online for the one problem. So let me share it with you.
By any chance, did you actually did they email you, or were you able to find a solution to the one I asked as well, or no?
To the one to the one with the hydrogen and the heat of hydrogen, or the heat of hydration one.
Yeah.
They never replied to my email. So I'll send another email tonight and see if they'll reply to it. But they never replied to it.
Okay.
Yeah. So I'll send them another email and see if they reply to that one.
Oh, the one in the vapor. Yes.
So I found the solution online. So at least we have the solution. So I guess it's like this is the mole fraction of cyclohexane in the vapor is the partial pressure of the, so it's like, okay, so you would use the equation that was like P total equals the mole fraction times PC. And so you would use that one, and then to isolate the mole fraction of cyclohexane, because this is like the partial pressure of cyclohexane, you would do mole fraction of cyclohexane equals P, wait, is it PT over PC? Oh, sorry. So this is when they're saying PT, they're actually saying, so it's like, okay, so it's equals. This is for the solution. So they're calling that one PC, and then this one is for the P of pure cyclohexane. And so that's what they're calling PT, I think, in this expression. And so to isolate this, you would do the partial pressure of cyclohexane divided by the pure pressure. I think.
That's so mean.
And so this is what you do. So you would do to figure out the total pressure of the solution, to do the cyclohexane and acetone. Yeah. You'd find the total pressure first. So you have those
So you basically like continue doing the normal finding the total pressure equation, and then right you have to be like, oh wait, it's
Yeah.
PC over PT. So the PC is only the partial pressure of the cyclohexane over the total pressure. So you need to find two. But, wow,
so that's what it is.
All right.
Yeah, so that's the solution to this one. I'll email them again about when you had a question about the PowerPoint presentation, but I'm like 99.9% sure they wrote the wrong answer and that our answer is correct on there for like when we both got 2 times 10 to the negative something, but they had like
I feel like it was like a rounding error that they did.
think I'm like 99% sure that we're both correct on that and that they must have just written the wrong answer on it because they didn't reply to that email either. But I'll send them both emails and see if they replied to tonight about problems. And I'll keep you guys posted. But yeah, they didn't reply to either of those. But I'm pretty sure that one's right. I'm still not sure about the heat of hydration one that Kelly asked though, because I feel like based on the equations, I'm not sure how that would have been negative, but it seems weird that that would be like a mistake. Like I feel like for like the PowerPoint presentation, it probably was just like a typo type situation. But for the other one, I'm like, I don't know how.
Yeah, I don't know. I don't know if they like did it a different way or what, but
Or if like there's reasoning for why it's negative versus why not. So I'll try to send them another email and see if they reply. And I'll BCC you guys this time so that if they do reply. Actually, if they reply, I won't reply to you guys. But anyhow, I'll let you guys know if they replied to the emails tonight.
Thank you.
Yeah, of course. Let me know if you have any like last minute questions or anything while you're studying tonight.
I have actually 2 last minute questions.
Oh yeah.
From the mock exam, I don't know if you have it in front of you. Could you by any chance explain 30 and 39?
Yeah, so for 30.
No, wait, it's 38, or I don't know, like it's different for here. Is it 37 maybe? Because I know like the number is a little different.
38 there. So 30. What is it on the mock exam? It's 38 on the mock exam.
Yeah.
They're gonna be 37 here, right?
Yeah.
Okay, so is it this one?
Mm-hmm.
Okay, so for this one.
Wait, no, this is still the I'm talking about the take home.
Oh, okay, sorry.
That's okay. Maybe I thought I like said that earlier. Maybe I was like confused.
No, I might have just missed it. There's like so many things that are like titled so similarly. So let me open the take home. Okay, so for 37. This one?
Yeah.
Okay, so for this one for voltaic cells, okay, so for voltaic cells, those are the ones, voltaic cells are the ones that don't have, so there's voltaic cells, and then the other name is slipping my mind, but there's one type of cell that where like you have to pump in the electron voltage. That's not voltaic cells. Voltaic cells, like they're spontaneous, they function by themselves without having anything. So here's like an illustration of a voltaic cell. And then here's our electrode. So this side is this is our anode. This is our cathode. Okay, so for the first side, so okay, for the first one, not for the first side. For the first one, we have electrons flow from the anode to the cathode. So since the anode is the one being oxidized, it's the one producing electrons. And so the electrons are going to move in this direction from the anode to the cathode. And so that's why, since this one's being oxidized, this one's being reduced, it's going to flow in this direction. So that's A is true. For B, it says electrons flow from the more negatively charged electrode to the more positively charged electrode. And so that is true. And so if you see on like a lot of the illustrations, when they do like diagrams, they'll like label the anode as negative and the cathode as positive. And this is why. And the reason for that, I think it's kind of confusing because you're like, oh wait, it's being oxidized, so it's becoming more positive. But the way that you're supposed to think about it is like this side is the electron producer. And so it's like getting increasingly negative because it's producing electrons here. And this side is taking those electrons and it's making them zero. Like it's combining them with a proton to like just make them zero. And so that's why it's like this is going from a negatively charged side to a positively charged electrode. So I think it's kind of like somewhat counterintuitive because like the anode is being oxidized and the cathode is being reduced, but it's more in terms of like this side is the one that's producing electrons, so it's negative, and this is the side that's like neutralizing those electrons, so it's positive. And that's why if you have like when you're identifying the anode and the cathode, and it has like the minus and the plus sign on the like on the diagram, that's why it's the minus for the anode and the plus for the cathode. So that's why that one's true. And then its electrons flow from higher potential energy to lower potential energy. That's true because this side is producing way more electrons over here. And so when it's flowing from the anode to the cathode, it's flowing to the side that has like the lower energy because it has less electrons on the cathode side. So that's why that one's true. And so all these statements are true. Does that make sense?
Yeah, that actually makes a lot of sense. Thank
Okay.
you.
And then the other one was 30. This one was this 38.
Yeah.
Okay, so in an electrochemical cell, we have Q equals 0.01 and K equal 8.55. What can you conclude about both of them? So the answer is D. E cell and E cell are both positive. Okay, so this one comes from I think. So we have K. So we have let me just pull up the equations that we have to work with. Okay, so here are the equations. Okay, so we have there all of this. So here are our equations. Okay, so for this one, for E cell, when we have so E cell, E like standard is E standard equals 0.0592 divided by N equals log of K. And so if we plug in, because N is always going to be positive, it shouldn't really matter what our like N value is. It should always give us, like, even if our N is 5 or if it's 2, whatever, it shouldn't really affect like if it's a positive or negative number. So we can just plug in 1 in there just to do the calculation. So if we do 0.0592 divided by 1 times log of 855, we get 0.17. So we get E standard is positive. So we can rule out. So E standard has to be positive, so it won't be this one or this one. So now we have to figure out what E cell is. So then we have E cell is E standard minus 0.592 times log of Q. And so let's see, so for log of Q, because Q is so small, so if we do log of 0.01, because it's negative, no matter what, because this log Q value, since our Q is less than 1, because it's -2 here, no matter what the value of n is, this whole thing is going to end up being positive. And we already said that our E cell was positive, and so you're going to end up doing a positive plus a positive, and you're going to get a positive E cell. Does that make sense?
Yeah, no, that actually makes a lot of sense. Thank you.
Okay. Yeah, of course.
I guess then my last question would be, do you mind sending, like, emailing the like KA, KB charts just in case?
Yeah, for sure.
Thank you.
Yeah. Do you have access to the textbook?
I do.
Okay,
Yeah.
just make sure. So I can always share that textbook with you guys too if you want to. But yeah, I can just send you the screenshots of those, the KA and KB and KF and KSP and everything else, just in case.
And then you said this will be posted, like, is it right after the session or like just later on today? Like,
So I can post the solutions like right now. The Zoom recording sometimes takes like an hour to like render and stuff. So as soon as it's posted, it can be done. But I can upload the worked out solutions like right now, so you guys have access to them.
okay, no problem. Thank you so much.
Yeah, of course. Any other questions or anything?
I'm good.
Okay. And if anything comes up tonight, feel totally free just to shoot me an email, and then I'll probably be around and can answer.
I was wondering if you could quickly go over question 27.
Yeah. So the take home are from the
Take home.
okay. So all right. The worked out solutions are, I just posted them if you wanted to go through the worked out solutions, Kelly. And then I'll post the recording as soon as it's finished.
Thank you.
Yeah, of course. Okay, so for the take home 27, you said? So I think that'll be 26 on this page. This one here?
No, like it's actually 27.
Oh, sorry. Okay, this one?
Yeah. So
Okay.
we narrowed it down to A and D, but the correct answer is A. So I was wondering if you could like explain like how to figure out the percent ionization based on like the information given.
Okay, so we have the solutions. And so I think that you would for percent ionization, I think you would have to just do the calculation for percent ionization in order to figure that out. I'm not sure that you'd be able to figure it out without doing the calculation for percent ionization. So you could just do that by doing this, we need the Ka, but we could do it with like the Ka expression. I'm not sure if you'd be able to figure it out without doing the actual calculation. Okay, so here's acids and bases. I'll just grab HNO2. So the Ka is 4.6 times 10 to the negative 4. I'm wondering if there, I feel like it's weird because like all of the multiple choice questions come from like the end of the chapter multiple choice stuff. And they usually give like the Kas and stuff there. So it's weird that you'd have to do the calculation, but I'm not sure how else you would know which one could have ionized more without doing the calculation. So for this then, because you have a Ka expression, it would be Ka equals x squared over your concentration of HNO2. And so if you do it for, so if you do 4.6 times 10 to the negative 4 times 1.25, and then you square root it, you would get x equals 0.2 or 0.02, sorry, 0.024 more. And so your percent ionization would be 0.024 divided by 1.25. And you'd get, if you do it times 100%, actually, so 100, then you get 1.9%.
Oh,
And then
okay.
if you do it for the other one, you do the exact same thing, but now you'd have your other concentration of HNO2, and then you would have 4.6 e to the negative 4 times 0.55, and then square root, and so you would get an X value of 0.016 molar. And then when you do 0.016 divided by 0.55 times 100, you get 2.9%. And so solution A, which is the one with this concentration, would have the higher percent ionization.
Okay. Oh, okay. So, like, how can I say this? So, I minus, like, there's like this equation on the textbook that involves like I, and like I found that to be the only equation that could lead me to percent ionization. But we could use like the concentration of H3O divided by the initial concentration used times 100 to get the percent ionization too.
Yeah, that's the percent ionization equation. I'm wondering what equation you're looking at. That is another equation for percent ionization.
The one that's like I minus 1 over I max minus 1.
Oh. I don't know. Is that what chapter is it in?
I think it's in that chapter. It was like in a picture. I did it based on memory. And that was like the first thing that came to my mind.
Oh, interesting. Yeah, I think that, I'm not sure. I think that you have to just do percent ionization like this in order to do it. But I think that in general, when you have these small Kas, the ones that have the smaller concentrations have the larger percent ionizations. So if you were out of time on an exam and you got this question, I would go for the one that had the smaller concentration.
Okay, thank you.
It's probably, if you have the time to do the calculation, I'd do the calculation, but it's like just from experience from doing these problems, I think that that's what it is. Any other questions though?
Can we go over number 8 as
Sure.
well?
Okay, so for this one, we have the plot showing the rate of decomposition of SO2 Cl2, and it's like really not important what the actual equation is, but the chart is the really important part here. This is the right problem, right? Yeah, okay. And so the important part is the chart here, and what's really important is that, okay, for a 0th order reaction, right? No matter what your concentration of SO2 Cl2 is, your rate is the same, right? And so if you had an equation that was 0 order, if you had a function that was 0 order, and you had rate times the concentration, so SO2Cl2. So even as the SO2Cl2 concentration increased, your rate would be the same all the time. So your 0th order like plot would look like this, right? Because a 0th order rate law is just rate equals K. It doesn't even matter what the concentration is. On the flip side, if you had a 2nd order reaction, your rate would be rate equals K, and then it would be SO2 Cl2 squared. And so this would be your rate here. This would be your concentration, SO2 Cl2. And so when your concentration was 1, you'd have a rate of 1, so we'll say like here. And then if you had a rate of 2, or sorry, if you have a concentration of 2, then you go 1, 2, 3, 4. And so then you would go up to 4 because you would do 2 squared is 4. And then if you had 3 here, then it would be 3 squared, so it would go to 9. So it would be like up here because you'd 5, 6, 7, 8, 9. So then it would be like here for 3. And so it'd end up actually forming a linear curve that was linear. And so it would, instead of being, it's kind of look straight here, but if you were to like really make this like actually plot it, because it's a squared function, it would be curved. So it would end up actually being like exponential, where it would be like this.
Oh, okay.
So for a first order reaction, your rate is your constant K times SO2 Cl2. And so basically, like, this is your X here, and this is your Y, and this is your slope. And the y-intercept is just 0. And so for this one, like as your concentration increases, it's just increasing linearly. And so that's why you just have a line here. And so if it were 0, if it looked like this, it would be a 0th order plot. If it looked like this, it would be a 2nd order plot. But if it's just totally linear, it would just be a 1st order plot, because all you're looking at is like the rate versus the concentration. Does that make sense?
Yes, it does. Thank you.
Yeah, of course. Any other problems you want to go over?
Those were it. Thank you.
Yeah, of course. Good luck. And let me know if you have any questions tonight. I'll email Dr. Munoz and Dr. Altinez again, and I'll let you guys know if they reply. Hopefully they will. All right.
Thank you.
Yeah, of course. Good luck. I'm sure you guys both do so well. I'm sure you'll do great tomorrow.